Hello! So, I'm going to record a lecture today. The reason I'm going to do so is because I will be gone this coming weekend, including Friday and Monday. As a consequence, I'd like to give you guys some things to think about. So with that said, what I'd like to introduce today is the idea of inverse trigonometry. And I'll get to this lecture also in class, but yeah, it's always nice to see something for the second time. So let's do some inverse trigonometry. So, let's suppose I ask you to solve an equation like sine of x equal to 1/8. It's too hard to do right now. We don't have any techniques appropriate to that challenge. Yeah, that's a little better. But in order to motivate how to solve that equation, let's think about what we did a while ago when we wanted to solve exponential equations. Let's suppose you wanted to solve 3 to the x is equal to 7. Now, when we first wrote down an equation like that, we didn't have any tools to use. We didn't have a technique to solve it. But then we introduced an inverse to this exponential function, the logarithm. So you can apply that inverse function to both sides of the equation, and you just get x equal to log base 3, 7. So the point is, if you want to solve exponential functions, you need inverses to exponential functions, i.e. logarithmic functions. So if we want to solve trig functions, we need inverses to trig functions, and that's what we'll develop this time. So, well, a lot of that is summarized up here also, so maybe I'll do that in class. But so we want to think about inverse functions. So here's the graph of sine of x, and y equal to the cosine of x. Now, check these out. Are these things one-to-one? Remember, you can check for one-to-oneness by the horizontal line test. So imagine drawing some horizontal lines and asking how many times does this horizontal line intersect that graph. And there we go, there's a horizontal line. It seems to intersect that graph at least 4 times. 4 times in this picture alone, and, well, really infinitely many times. If we kept on going in either direction, we would see infinitely many points of intersection. So, are these functions one-to-one? No. So do they have inverse functions? No. One-to-one functions are the things that have inverse functions. So there's already something that's really wacky here. I want to find inverses to trig functions, but trig functions don't have inverses. So in order to figure out a way to get around that problem, let's think about another circumstance where there isn't an inverse function, and yet nonetheless we made up a name for an inverse function. So there's the graph of g of x equal to x squared. Here's the graph of y equals x squared. Is this function one-to-one? And the answer, of course, is still no. You draw a horizontal line. You see 2 points of intersection. So does this have an inverse function? No. And yet you know an inverse function for this function. It's called the square root function. And, well, how do you build it? Well, what you can do is you can take the restriction of g of x equal to x squared to the domain 0 to infinity. So I'm only going to think about x values that are positive. Does that function pass the horizontal line test? Yeah. You draw any horizontal line, hey look, they all cross the graph in either 1 or 0 points. So does it have an inverse function? Yeah, it has an inverse function. And you already know the name for this inverse function. The inverse function is the square root function. So when you encounter a function that's not one-to-one, but whose inverse you would like to take anyway, what you can do is you can restrict the domain to a smaller set over which the function is one-to-one. So here's this exactly. Here's the graph of y equal to sine of x, plotted from negative pi over 2 to pi over 2. So I'm going to restrict the domain. I'm going to take the formula y equal to sine of x, but I'm going to say I'm only going to plug in numbers that are between negative pi over 2 and pi over 2. There's the graph of cosine of x, but I'm going to restrict its domain. I'm only going to allow x values between 0 and pi. And now let's just read off the range. What y values do you see? Well, it looks like the most negative y value is -1, the most positive is 1. So the range is -1 to 1. Similarly, the range of cosine is -1 to 1. Now look at those graphs. Do those graphs pass the horizontal line test? They do, right? You draw horizontal lines? Yeah, all of these horizontal lines intersect the graph in either 0 or 1 point. Same thing with cosine. So are these things 1 to 1? Yes. So do they have inverse functions? Yes, they do. Okay, so as long as we restrict domains appropriately, trig functions have inverse functions. Let's give them names. Inverse sine of x, also called arc sine of x. Importantly, lots of your calculators or computing devices might read an arc sine instead of a sine. You might have to ask it what arc sine is instead of sine inverse. Is the inverse to sine of x, but after you restrict its domain to -pi/2 to pi/2. So you restrict the domain to a domain over which sine is injective, so you can take an inverse. Then you take the inverse. That's what arc sine is. Inverse cosine, also called arc cosine, is the inverse to cosine after you restrict the domain to 0, pi. Alright, so, well, we can read some things about this function already. What's the domain of inverse sine? Well, the domain of inverse sine, this should be the same thing as the range of sine. And, well, check it out, that's what we inverted. It had range -1 to 1, so its inverse function will have a domain -1 to 1. Similarly, what's the domain of inverse cosine? The domain of inverse cosine is -1 to 1. So maybe I'll say something explicitly in here. If someone asks you to evaluate inverse cosine of 2, well, you can't. Inverse cosine of 2 doesn't exist. 2 is not in the domain. If you make it to the end of the video and the pets that you're hearing are still in the room, you'll get to meet some of the pets that are in this room. Presently, there are 2. Okay, let's play the same game with ranges. What's the range of inverse sine? The range of inverse sine should be the same as the domain of sine after you've restricted the domain. We restricted the domain to -pi/2 to pi/2. So this domain is the same as the range of the inverse function. So the range of inverse sine is -pi/2 to pi/2. What's the range of inverse cosine? It's the same as the domain of cosine after you restrict the domain. So the range of inverse cosine is 0 to pi. Cool. So, let's just continue studying these inverse trig functions for a little bit. So the first thing you might want to do is evaluate them. No, that's the second thing we'll do. First we'll graph them. Let's graph these things. So remember, how does the graph of the inverse function differ from the graph of the original function? The graph of the inverse function is the same as the graph of the original with x and y coordinates flipped. What does that mean? Well, here's the graph of y equal to the sine of x. So the inverse sine of x should have the exact same graph as this, but with x, y values switched. So let's see, this point at 0, 0 is going to wind up at the point at 0, 0, because you're going to flip the xy coordinate and get that same point back. that point at negative pi over 2 comma negative 1 is going to end up at negative 1 comma negative pi over 2. It's basically horizontal here, so close to this point it will be basically vertical. It will come in, it'll meet the origin, it'll call it back out. So there's a graph of y equal to sine inverse of x, or y equal to arcsine of x. Same thing with cosine. This point at 0, 1 will go to a point at 1, 0. This point at pi comma negative 1 will land at the point this y value is 0. And pi over 2, Chris. Well, hopefully that's been the false typo today. So this point at pi over 2 comma 0, this point, is going to end up at the point 0 comma pi over 2. This point at pi negative 1 will end up at negative 1 pi, and then I'll do the exact same thing. There's the graph of inverse cosine. Nice. So let's just start translating this a little bit. Right, it'll be awkward if we want to make computations if we have to remember the philosophy of inverse functions every time we want to make the computations. So let's just pre-can the philosophy of inverse functions and write it down as a definition. So if I give you any x value between negative 1 and 1, then if I say inverse sine of x is equal to theta, what does that mean? Well, that means sine of theta is equal to x. And it also means that theta is in the range of inverse sine. And what's the range of inverse sine? It's negative pi over 2 to pi over 2. Similarly, if I give you an x value and say that inverse cosine of that x value is equal to theta, that means cosine of theta is equal to that x value, and theta is in the range of inverse cosine. So theta is between 0 and pi. So let's play the game a little bit. So let's start here. Think for a moment and find for me an angle, theta, between 0 and pi which satisfies cosine of theta is equal to 1/2. And to do that, take a look at a unit circle. If you've got one just handy, use it. Otherwise, here, I'll draw a unit circle. Angle of 0 radians lands you at 1, 0. Pi over 4 lands you at root 2 over 2, comma root 2 over 2. An angle of pi over 6, I really should be using multiple colors, lands you at root 3 over 2, comma 1 over 2. An angle of pi over 3, oh, that pen's dead. An angle of pi over 3 lands you at 1/2, comma root 3 over 2. Angle of pi over 2, a right angle, lands you at 0, 1. Well, I guess, as is, the color coding didn't help because I didn't use it effectively. That's okay. So, let's go back to this. So find me an angle between 0 and pi which satisfies cosine is equal to 1/2. Alright. So which of these angles between 0 and pi, actually they're all between 0 and pi over 2, result in a cosine of 1/2? Right, cosine is the x value. There, I see an x value of 1/2, corresponding to an angle of pi over 3. Theta equal to pi over 3 definitely has cosine equal to 1/2. Is that angle between 0 and pi? Yeah, it is. Right? It's bigger than 0 and less than pi. So what does that mean? That means that inverse cosine of 1/2 is equal to pi over 3. Inverse cosine of 1/2 is pi over 3. And, right, so I plan on filling in a table. Inverse cosine of 1/2 is pi over 3. Again. Find for me an angle between negative pi over 2 and pi over 2, which satisfies sine of theta is equal to negative 1/2. So let's keep on looking at this unit circle. So let's see, I'm looking for a negative y value. So it looks like I need something to the south of the x-axis. Alright, so now, take a look. You want to get sine of theta equal to 1/2. So, sine of theta, that's the y-coordinate, and I need it to be 1/2. Well, there's a place where y is equal to 1/2, so apparently this angle is the one we want. And if you look at the unit circle that's, say, handed out in class, you would say, well, that's like 11 pi over 6. So there's an initial guess made by the phrasing I'm using. It's clear that that's wrong. So let's check that. It definitely has sine equal to negative 1/2. Is it between negative pi over 2 and pi over 2, though? Well, it's not. This is almost 2 pi. Okay, but that's like definitely the angle we want. We just want a different way of writing it. Instead of rotating forward by 11 pi over 6, how far do you rotate backwards? Rotate backwards by negative pi over 6. So, second guess, negative pi over 6. It still has the correct trig function, so sine equal to a negative 1/2. Is this between negative pi over 2 and pi over 2? Yeah, it's pretty close to 0. So, that means inverse sine of negative 1 over 2 is equal to pi over 6. Inverse sine of negative 1 over 2 is equal to, no, negative pi over 6, dummy. Cool. So, what I'll have you do in class is fill out this table and just take a while to do it. Since there's not really the same freedom of interaction here, I'll encourage you to pause the video, think through these computations, figure out what they have to be, and then resume. But in the meantime, I guess I'll talk through it. So, let's start at the top. Let's figure out what inverse cosine of 1 should be. So to figure out inverse cosine of 1, to do that, I need to figure out when is cosine of theta equal to 1, and I need to make sure to use an angle that's between 0 and pi. Well, I want x to be equal to 1. X is cosine. Well, that looks like it happens at an angle of 0. In fact, maybe you notice, I'm just going to start tracing up this way. If I want to find the inverse cosine of root 3 over 2, apparently it's pi over 6. So cosine of pi over 6 is root 3 over 2, and this is definitely between 0 and pi. Alright, now let's get to some negative numbers and see what happens. Let's see, we've got 2 pi over 3 3 pi over 4, 5 pi over 6, at an angle of pi, negative 1/2, root 3 over 2, cool. So if I want to figure out inverse cosine of negative 1/2, there's an x value of negative 1/2. It corresponds to an angle of 2 pi over 3. That's between 0 and pi. Nice. And those are just, in some sense, we maybe didn't even need to fill in this whole table. That whole table is encoded in the unit circle. Let's play the same game for sine. So, well, maybe I'll say a few more words. So I want a number between negative pi halves and pi halves where sine is equal to 1. What number do you think of when I describe that? Yeah, you think of a right angle, pi over 2. Sine of pi over 2 is 1. Sine of pi over 3 is root 3 over 2. Inverse sine of root 2 over 2 is pi over 4. Inverse sine of 1/2 is pi over 6. Inverse sine of 0, well, the sine of 0 is 0, so inverse sine of 0 should also be 0. And let's keep counting back. Negative pi over 6 brought us to a y value of negative 1/2, an angle of negative pi over 4. Let me cross that out, I don't need that today. Negative pi over 4 gave us negative root 2 over 2, so inverse sine of negative root 2 over 2 should be negative pi over 4. Inverse sine of negative root 3 over 2 will be this angle, negative pi over 3. Inverse sine of negative 1 will be negative pi over 2. Cool. And right, this is when I would probably pause for questions, but presumably what you've done is you've filled in that table by doing almost exactly what I talked through right there, and then maybe watched what I just said at double speed or skipped ahead. So let's keep it going. So we know how to evaluate inverse trig functions. Let's try to get some facts about inverse trig functions. So by looking at that table, tell me what's the cosine of the inverse cosine of 1/2? Well, from the inside out, the inverse cosine of 1/2 is pi over 3. So it's the cosine of pi over 3. The cosine of pi over 3 is 1/2. Well, wait. Like, that was silly, right? Like, I repeated walk that I did twice. Because why was the inverse cosine of 1/2 pi over 3? It was because the cosine of pi over 3 is 1/2. So, there should be some, like this is what the answer had to be. Let's play again. The inverse sine of the sine of negative 1. Well, the sine of the inverse sine of negative 1. I think I said that in the opposite order. So the inverse sine of negative 1 is negative pi over 2. So I have to compute the sine of negative pi over 2. So that's the sine of a negative right angle? Yeah, that's negative 1. Something that seems pretty convincing here. Looks a lot like the cosine of the inverse cosine of a thing is always just that thing. The cosine of the inverse cosine of x is always x. The sine of the inverse sine of x is always x. Then maybe I'll put that in emphasis. So what does that say? Let's see what it says by trying to see what it can't say. What's the cosine of the inverse cosine of 2? Well, evaluating it from the inside out, inverse cosine of 2 doesn't exist. 2 is not in the domain of inverse cosine. I'll use that sloppy abbreviation of DNE for does not exist. if you take an x value that's not even in the domain of consideration, the output can't be x. It's just nothing. Okay, cool. Let's go the other way around. Surely that'll just always be x also. Let's compute the inverse cosine of the cosine of 3 pi. So let's play that game. What's the cosine of 3 pi? So let's see. The cosine of 1 pi, 2 pi, 3 pi is -1. So I want the inverse cosine of -1. The inverse cosine of -1 is pi. That's weird. Again, the inverse sine of the sine of 5 pi over 3. So let's see, 5 pi over 3. 2 pi over 3, 3 pi over 3, 4 pi over 3. This is 5 pi over 3. Results in a point of 1/2 comma -√3 over 2. So, the sine of 5 pi over 3 is -√3 over 2. The inverse sine of -√3 over 2 Well, hopefully you guys noticed that. That should have been a pi over 3, shouldn't it have? Notice these aren't the same. So is the inverse sine of the sine of an angle always that same angle? Nope. It's just some angle with the same sine or cosine value. And we'll come back to exactly how you evaluate then those things if they don't just always equal out to the same as the input. So let's think about what inverse sine means a little bit more. So you should think of inverse sine of a number as being like, I want to start with the y-coordinate and see what rotation gives you that y-coordinate. But the rotation has to be in the range of inverse sine. So the rotation has to be between -pi over 2 and pi over 2. So if you want to evaluate inverse sine of y, you need to figure out what rotation between -pi over 2 and pi over 2 produces that y-coordinate. Similarly, think about inverse cosine of x as being the answer to the question, what rotation between 0 and pi gives the desired x-coordinate. And why between 0 and pi? Well, it's because the range of inverse cosine is 0 to pi. Why was this -pi over 2 to pi over 2? Because the range of inverse sine is -pi over 2 to pi over 2. So let's trace out what angles those are. So the range of inverse sine is -pi over 2 to pi over 2. So there's -pi over 2 to pi over 2 and all the angles between them. You're hearing a cat. Yeah, that's what an interpreter. Yeah, that's a good cat. This is a very sophisticated recording setup I have on top of their cat tower. Alright. Similarly, what's the range of inverse cosine? The range of inverse cosine is angles between 0 and pi. There's an angle of 0, there's an angle of pi. I want the angles between. So, inverse sine of y is equal to theta means that theta is